And welcome to the second half of Chapter 5. Really, this is the third video in the series, but really it's the second half of this chapter. And we're going to continue our discussion on reducing down circuits, minimizing the number of gates that we need, and potentially the number of inputs. Sometimes we have a circuit built and one input has no effect on the output whatsoever, and so we can actually remove it from the system. So let's go ahead and start with the universal capability of NAND and NOR gates. And so I don't believe I've discussed this just quite yet, but one way that we could create an inverter is with a NAND gate. And the way we do that is we tie both inputs to the same output. Because this is the equation that you would get, right? So this is a NAND. So anything ANDed with itself is itself, and then you have the inversion. So it's always going to be the opposite of whatever it is. If you have 0, 0 on the input, that's going to give you a 0 from the AND, and the inverter will give it a 1, and so that acts like an inverter. So this is the idea behind the universal capability of using NAND gates and NOR gates, is that really, I know this is just an example on an inverter, but you can convert, or you can use NAND gates and NOR gates for any gate that you can think of. Okay, and so it goes along with the bubble pushing, and knowing essentially what the logic truth table should be, and then using NAND gates and NOR gates as an inverter, right? Or as using it as the NAND or the NOR gate. So and the idea is that we can make any of the gates if we just use NAND and NORs, right? So if you wanted to, you could stockpile NAND and NORs and create any of the other gates. So here we go. Using the same concept that we can make an inverter out of a NAND gate or a NOR gate, either way, look at this. So if we have a NAND configuration here, if all we're using is NAND gates, then if we wanted to AND these two together, we'd have to send it through a NAND gate first and then negate this inversion on the outside. So that's like a double inversion on an AND, and so you're left with an AND here. Okay, so the same thing can happen for a NOR, right? A NOR can be used as an inverter in the same way. I know it's on a few slides from now, but it'll work the same way, where you tie both of the inputs of the gate to one single input, and then it acts like an inverter as well. So in the same fashion, we're going to see that you can convert two NOR gates cascaded into one another and make an OR out of that. So here we go. In this case, this is an OR gate created from strictly NANDs, right? So here we have an inversion. Here we have an inversion. And so essentially we have if we were going to write this, we would have an inversion bubble here and here and here. Okay, we know from if we were to do the truth table on this and knowing our Boolean algebra based on this, right? So you have an inverted A out of this gate, you have an inverted B out of this gate, and then you have inverted A and inverted B NANDed together. And when you do the Morgans on it, break the bar, change the sign, you'll have double prime A plus double prime B, and then the doubles will cancel, and you're left with A or B. Okay, so that's what that kind of explains the universality of these NAND and NOR gates. So here's a NOR. So you can see we have this configuration here, and so if you take the OR gate and you negate the end, you come up with a NOR. So if I were drawing a picture, I would have the OR gate kind of around here, and then this would be the inversion bubble on the outside, right? So there's the NOR, and again, if you were to do the output of each one of these gates and do the Booleans or the De Morgans in this case, well, you'd have to do both, right? Because anytime you invert the output, now you have to do De Morgans at least once, and so you'll use a combination of your early Chapter 5 techniques to come up with the NOR gate here. Okay. So again, if you do this with a NOR gate, all right, you have the same thing. You have either a 0, 0, which is a 0 on the OR, and then it inverts to a 1, or you have 1, 1, which gives you a high, and then it will invert to a low. So in both cases, you have an inversion. So It looks exactly the same as at least how you wire it, as the NAND gate. Okay, and so it suggests here, form the other logic gates using only NORs. So try and see if you can come up with that, and you can email me your results if you do. I always like to see if people can get those. Okay, and so you may even have a test question or a quiz question that looks into this. Okay, using the other gates. So let me know if you have any questions on that. Another way that we can simplify things to some degree is to create, if we have a product of sums, POS form. So that's where we have, it looks like one big foil, right? You have some quantity where two variables are added together, times some other quantity where you have variables added together, times some other quantity where you have variables added together. That's called the product of sums form, right? That's a little bit different than the sum of products. So sum of products is what we want to get our equations into to do K-maps, which is what we're getting ready to talk about. So in this format, this is like the unexpanded foil. That's the way I always think about it. But it's just we call it the POS form, and then the other direction is SOP. You don't necessarily have to remember that, but the AND or invert. So you only use AND gates, OR gates, or invert gates. And the invert gates you just use as little bubbles, either on the input or the output. And that can describe all circuits, okay? And obviously the other way to do it would be to expand that out. If you were to foil this and have not AC plus BC plus, not AC plus not A, not D, plus BC plus B, not D, right? And so if we were to write it the other way, this is how it would look. So this produces the same output as this. Now, in this case, you can see that we have sort of gotten away with some fewer gates, but we're also, in a little bit different format here that might not lend itself to what we're about to do very well. So we want to get it into sum of products form before we do our K-maps, and it'll make everything so much easier. So you can see here we're using 1, 2, 3, 4, 5 gates, as opposed to in this situation we had 3. Okay. So the next thing we're going to talk about in terms of reducing the number of gates, right? That's the theme of chapter 5, is we want to minimize the number of gates because it does all of those things here. It reduces the circuit cost. And when you don't have as many gates, you don't need as many chips, and that means you can reduce the physical footprint on the circuit board. And when you don't have as many things to wire up and you don't have as many gates, obviously you don't have as many things that can go wrong in terms of gate failures. Okay, now it does require a sum of products form. So if you're given an equation that's not all in a sum of products form and it still has some quantities that need to be multiplied together, multiply those first. That doesn't mean that you should use Boolean algebra and try to reduce it. The whole point of the K-map is to do that reducing for you. So if it's some big, long equation, x equals a bunch of different, this plus this plus this plus this plus this, that's fine. Because all you're going to do is mark a 1 in the map itself. Okay? So the idea here is that instead of using our mathematical skills, we're going to do it graphically. And so what we do with the K-map is we show all possible output, or all output levels for every possible input combination. So if we only have 2, then that's a 2 by 2. Essentially, you could think about it like a little Excel sheet, right? It looks like a table. Because the only possibilities are 0, 0, 0, 1, 1, 0, or 1, 1. And so you only need 4 possible outputs on the table. Every time that you increase the number of inputs, that's going to rise for 2 to the n. So if you have 3 variables, you're going all the way from 0, 0, 0 to 1, 1, 1, and in which case you need 8. So you could have a, there's a few different ways that you can write it, and I'll show you once I get to the board, because it's hard to describe it when I don't have it in front of me, so I can point to it. All right, so here's what we're doing. We're going to transform the Boolean equation into an SOP form. Sometimes I give this to you. Sometimes I just give you the circuit, and you have to come up with the SOP form. Then you're going to fill in the appropriate cells of the K-map. I'm only going to make you put in where it's high. I'm not going to also make you put in where it's low, because all we care about is where it's high. And then we're going to encircle adjacent cells, so it's kind of like a little game almost. I always thought it was like a game when I learned this. But encircle adjacent cells in groups of 2, 4, or 8. And so you have to watch for the wraparound from top to bottom and from left to right. You have to assume that the table connects on the right side to the left side if you were to make a 3D shape out of it. And the same goes for the top line to the bottom line. If you were to bend the piece of paper that's got the table on it and make the ends touch, then the top to the bottom you can also circle within there as well. It's just kind of an out-of-the-box way to think about it. So this is what we are going to start with right here. And I'm going to go from the board for the rest of the time. And I have this written on the board already. We're going to look at the output of each one of these gates. We're going to come up with the Boolean equation and in the SOP form, and then we're going to draw our K-map. Okay, and this is the example from the PowerPoint. And what we're going to do is look at the output of each one of these gates and come up with an equation that solves for output X. And then we will do a K-map to simplify this instead of using the first part of Chapter 5 where we talked about Boolean algebra and reducing it using the laws and techniques from that portion of the chapter. So these are NOR gates. This is an OR, and this is an AND. So up here, I've got A plus B, the whole thing knotted. This one, I've got B plus C, the whole thing knotted. And then out of here, I'm NORing them both together. So I've got A plus B, the whole thing knotted, plus B plus C, the whole thing knotted, and then all of it knotted because that's a NOR. Out of this one, I take the D and AND it with this. So this is D and the NOR of B plus C. And so then finally I have an equation that looks like this. X equals and that is this, and that with a plus in between, and then plus, because this is an OR, D times B plus C. Now, as I said before, you don't want to use Boolean to get to the final answer, okay? But to get to a sum of products form, you at least have to do De Morgan's and get rid of those inversions, okay? So that's what we're going to do. We just want to get it into a sum of products form. So I'm going to do De Morgan's here, and I'll do a De Morgan's here. So break the bar, change the sign. So now I've got A plus B double prime times B plus C double prime plus D times, break the bar, change the sign, B naught, C naught. Okay? So now this is going to, the double bars are going to cancel here, the double bars are cancel here, and so I've got a FOIL situation, so I'm just going to go ahead and write this all out. So I'm going to have AB. Remember, those double bars are gone now because double inversion goes back to the original. So AB plus AC plus B, there is no squared, right? We just write that as B times B because it's an AND, it's logic, plus BC plus B naught, C naught, D. Okay, and that is our equation for X. All right, so now what I'm going to do is I'm going to erase the circuit up here. And I'm going to redraw what we just came up with. So X equals AB plus AC plus BB plus BC plus B naught, C naught, D. Okay, now we can erase the rest of it so I can have some room. So when you draw a K-map, the size of the table is dependent on how many inputs that you have. So if you have two inputs, let's say you had A and B, what are all the possible combinations? There are 0, 0, 0, 1, 1, 0, 1, 1. There are 4 possible combinations. So you need to have a grid of 4. if you have 3 of them, and so A, B, C, you're going from 0, 0, 0 to 1, 1, 1. That's 8, right? So you need 1. And it doesn't matter if you do this vertically or horizontally. You have to have a group of 8. If you have 4 inputs, which is what we have, then you have 16 possible combinations, and so you need to have a grid that's 4 by 4. So we'll do. Okay, and the size of this grid is always 2 to the n, where n equals the number of inputs. Okay, 2 to the n. So in this case we have 4, so 2 to the 4th is 16. All right. Now the way I label the headers on the columns and the rows is that I have to go, if I'm going from here to here, or if I'm going from some box in this column to a box in this column, or vice versa, only one number, not one number, but only one input can change whether it's high or low. All right, so let me show you what I mean by that. So normally when we count in binary, we would say something like A naught, B naught, A naught B, A B naught, and then AB, right? To represent 0, 0, 0, 1, 1, 0, 1, 1. That's how we count in binary. However, you can't use that as the headers here, because if you notice from here to here, there's only one input that changes, right? And that's B. But from here to there, we're changing both of those, and so it won't work if you do that. So the way that I set this up is I always start with the 0, 0, and then the 0, 1, and then the 1, 1, because now A is the only one that changes from here to here. And then finally A, A B naught. Okay? So the count actually goes 0, 0, 0, 1, 1, 1, 1, 0. Right? So that looks more like gray code, where you're only changing one digit at a time. Okay? And so here's the thing, is I always start with 0, 0, but you could start with whatever you want. You could start with this, and then your next one would be this, as long as, or you could go the other way. It doesn't matter. But the sequence will always follow this, okay, whether forwards or backwards. And here's the thing. Whatever you do on your row headers here, you have to do the same thing for up here on your column headers. And so if these are going to represent C and D, then the first one is C naught, D naught. The next one will be C naught, D. The next one's CD. And the next one is CD naught. So it doesn't matter which way you do this, as long as only one digit changes from row to row. And also, the columns have to match, the column headers have to match the pattern that you made over here. Okay? So it couldn't be simpler, and I think this is why some people prefer K-maps as opposed to the Boolean, because you don't have to do any math here. All you have to do is say, where is X high, right? And then just put that on the graph and just represent it with a 1, or you could do high or put an X there or whatever you want to do. I typically just put a 1 in there. The other thing is, because in the sum of products form, you typically have a lot of terms added together, you want to make sure that you don't forget any, because once you get into like 2, 3, 4, and you have a lot of 1s on the board, sometimes it's hard to remember where you're at. So I always mark which ones I'm done with. Okay, so the first one is where X is high when A and B are both high. So where is A and B high? Well, that's this whole row right here, right? And so this term right here says that C and D don't matter at all as long as A and B are high, right? And that's the whole purpose of ORing these all together, because any one of them will cause the output to go high. So I put 1s in here for the whole row. Okay? All right, so I'm done with that one. The next one is where A is high and C is high. So let's see where that is. So A is high on the bottom 2 rows. C is high on the far 2 columns. which means we're talking about this 4x4 here, okay? And it says that B doesn't matter and D doesn't matter, so it's all 4 of these. And 2 of them have already been completed by the last one. So already you can see we've got some overlap here. These are not unique. Some of them, can be, like obviously you could see here, like B, BC, AB. Those all could have a B pulled out, and you'd be left with a bunch of stuff plus 1. So just kind of looking into it with our first half of chapter 5 techniques, you can see that this needs to be reduced. Okay, but you'll see how we do that with the K-map. Okay, so AC is done. All the places where A is high and C is high. And as you know, this is just B. So this is great when you get a single letter input, because then you can put a whole bunch of ones in. So this says, regardless of A and C and D, whenever B itself is high, all of those outputs are high. So that's these 2 rows. Now half of that's already been taken up, but there we go. All right, so that accounts for B. All right, so I'm going to go ahead and check that off. Now we have B and C, which we've already covered because we went ahead and did all of the spots that are where B is high. And that just so happens to cover, C is high in these 2 columns. So we're talking about these 4 right here with this, but this one covers the whole 2 rows. Okay, so that one's done already. And then the last one's a little bit more specific. B naught and C naught and D. All right, well, where is C naught and D? That's this entire column. And then we're refining it to only talk about B naught. So that's this column and this row and this bottom row where you have B naught. So that is this one and this one. This term right here refers to this and this, which one of them has already been done with a different term. So here we go. All right. So now I've got them all. Okay. So now what I'm trying to do is I'm trying to make of 8, 4, and 2. You can't do 6. You can't do 3. You can't go diagonal. This isn't like bingo. You can only do groups of 8 and 2. Okay. So the biggest thing that I can draw, and I think that's pretty obvious, our discussion about a group of 8 right there in the middle. Okay, so that takes care of, what, 80% of them right there, right? Or close to it. So we just need now to get these other ones circled. Okay? So what you do is you try to draw the biggest box you can, and if you have to reuse something that's already been circled, that's fine. Okay? I think, well, I guess it doesn't matter which way, but I'm going to try to get these 2 in the same group and then reuse these to get it done. Okay, because that'll give me a group of 4. Whereas, remember, as I said, this side and this side, you have to think about them curling around and making a cylinder, because those 2 sides touch each other. So it would be, it's legal for me to do this and just circle those 2, because those 2 are touching together. That would be a group of 2, even though they're on the top and the bottom. Remember, you have to think about this thing touching around the outside. That's why, as long as you follow the pattern, it doesn't matter which one you start with. Okay? All right, well, the same is true for the other sides, the left and the right. So this side technically touches this side. So if there was a 1 here, I could circle that. All right, but I'm not going to circle this because I want to make a bigger, a bigger group of 4. So that's what I'll do. Oh, I want to do it with orange. Keep my colors straight. There we go. So now I just have to take care of this 1 that's left over. Okay? And I think the biggest thing I can draw is a group of 4. This way will give me 3, but we don't do groups of 3. But if I do this right here, that gives me a group of 4. So I think I'm going to circle that. Okay, that takes care of everything. So now I'm down to 3 separate terms. So now we say, here's the final equation. If I were to represent this group, what stays constant the whole time? Well, in these 2 rows, A changes, so A doesn't matter. In this group of 8, C and D also don't matter. The only thing that matters is that B is high. All right, so that's our first term. The second term, we'll do this column over here. And as you can see, C and D naught are the only things that remain constant, whereas it doesn't matter what combination of A and B you have, as long as this is true. So that's my second term, C, D naught. The last one is this group of 4 down here. And again, we ask ourselves, what remains constant? Well, in these 2 columns, the only thing that remains constant is C. And in these 2 rows, the only thing that remains constant is A. So that's plus AC. Okay? So there we go. We just reduced it without having to use Boolean algebra and the rules and all that good stuff. Okay? So, you know, some people like this better because it's graphical and they make too many mistakes with their Boolean algebra. But again, if I give you the circuit, you're still going to have to do some De Morgans to get to your sum of products form. Okay? All right, so I want to do, just to say one more thing here. If you were to create this circuit in Quartus and set that equal to X, and you have a different circuit right underneath that uses those same inputs, but then is attached to a different output, this X and Y should look identical in your vector waveform file in the simulation. Okay, so let's do another one, and I'm going to go out of the book for this. I just happen to have my book right here. We'll make our way over to chapter 5, if you're playing along at home. On page 225 at the top there for section 5.9, it says, using a Karnoff map, reduce the following equations to a minimum form. Okay. I'm going to do 538C, I think. Because usually the even numbers are a little bit more challenging, right? I'm sure you found that over the years. So this is 538, letter C. And so I'm going to need my book up here because it's kind of long. So Y equals A times C D naught plus C naught D naught. And that is plus A B naught D plus A naught B naught C D naught. Okay. So in this case, I'm not giving you the circuit, and then you have to figure out what the output of the gates are and then do De Morgans to get it down to this point. You do have to do a little bit of... So we do have to FOIL this term right here, but then we'll already be into an equation that we can go ahead and write a K-map for. So let me go ahead and do this algebra real quick. So here's A C D naught plus A C naught D naught plus A B naught D plus A naught B naught C D naught. There we go. Now we are into a sum of products form. So since we have 4 different inputs of A, B, C, D, I'm going to create a K-map of 16. And again, I'm just going to start, I typically start these the same way. A naught, B naught, A naught, B, A, B, A, B naught. So then over here, C naught, D naught, C naught, D, C, D, C, D naught. Okay. So again, we're just going to go along here, and for each term, we're going to write where that creates a high for this output. Okay, so for A, C, D, C, right, it would be the same thing. So A, C, D naught. A, this is where A is high, and then C, D naught is this column over here. So it's these 2 rows and this column, and so we're talking about just these two spots right here. All right, the next one is A, C naught, D naught. So C naught, D naught is this column right here, and then when you AND that with A, you're talking about just these two. There we go. Oh, I'm not marking them off as I go. I already had a moment of panic. Oh no, did I forget one? All right, so the next one is A, B naught, D. So A, B naught is this last row, and then you add the D, and that's these middle two. Okay, so there we go. And then finally, very specifically, whenever you have four inputs, or I'm sorry, four of the characters, right, in a single term, that means you're talking about one single spot. When you have three, you're talking about two spots. When you have two, you're talking about four spots. And when you have one, you're talking about 8 spots. So that's the most that you can get. All right, so for this one, we're talking about A naught, B naught, which is the top row, and then C, D naught, which is this one. So it's just this one single out here in the corner. Okay, that means that we have all of these done. And we need to start circling. Now we need the orange. Okay, something I want to point out here is that not only can you do groups of 8, 4, and 2 anywhere here and touching this way and touching this way. If you were to somehow like pull this corner around to this corner and this corner around to this corner and have them all meet, then this and this and this and this is possible to make a group of 4. So I'll say over here, don't forget to look for the 4 corners. Now, sometimes it's not going to help you, but don't forget to look, okay? So if I had a high in all 4 corners, I could group those together as one group of 4, all right? But I don't. I just wanted to point out that if you do encounter that, like on a quiz or an exam, that you'll know that you can use the 4 corners as well. And this one, I just want the black. There we go. Okay. So, I can't make any groups of 8. I think the biggest I can do is probably a group of 4, and I think I can do a couple of those. So here's what I see. I see this entire bottom row as a group of 4, and I think that's probably the most obvious to everyone. So let's go ahead and circle that. I've got 3 that I have to take care of now. And so I think that for this one and this one, I'm going to do a group of 4, right? These 2 and these 2, because if we pulled it around, they touch. So that gets rid of those 2 in one grouping, which leaves us with this one. And I do not believe that there's a way to make a group of 2, or I'm sorry, a group of 4 with this, because we don't have anything here, and we don't have a 4th corner. So I think the best we can do for this one is a group of 2, just like that. All right, now we have everything circled. It's time to go ahead and rewrite the equation. All right, so the first one was this down here, and as you can see, in this grouping, C and D don't matter. What matters is A high, B low. So that's the first term. Okay, the next term is this outside group of 4. And so what remains constant there between the 2 rows is A. So plus A times this column on the remains constant is D naught. So that's A D naught. Okay, finally we have this group of 2. So it's going to have 3 terms in it. And so what remains constant here is definitely C and D naught because it's in that single column. But then between these two rows, the only thing that remains constant is B naught. So B naught, C, D naught. And there we go. So that is the way, this is the reduced form of this up here. And if you wanted to double check yourself, you could always do the Boolean of this. Okay, so I can do that real quick. Okay, now I'm going to try to solve this with Boolean. And I'm going to go ahead and first thing is factor out the A D naught here. So A D naught, and I've got C plus C naught left over, plus A B naught D plus A naught B naught C D naught. So anything ORed with its complement is always a 1, and so that leaves me with A D naught plus A B naught D. And plus A naught, B naught, C, D naught. Okay, so now I'm going to try to look for something else. I'm going to try to use this because I can see maybe a rule 10. If I pull out, well, we would have it in this scenario and we would have it in this scenario here. Well, let's do it right here. So I'm going to pull an A out of these two terms. So I've got A times D naught plus, I'm going to put the D in front to make it more obvious, D and that plus this. And so rule 10 tells us that if we take the complement, if we take an input and take its or it with its complement, which happens to be ANDed with something, we can get rid of that complement here. So that's going to leave us with AD plus AAB, which I don't know why that's there, because that should have been pulled out. So we're just left with the B. So A, B naught plus, A naught, B, C, D naught. Oh, that's confusing. All right, so I think I can do something with this term over here, and another rule 10, where if I pull the B naught out, that's going to leave this A. So finally, equals AD plus, pull the B naught out, I'm left with A plus A naught, C D naught. Using rule 10, that becomes A D naught plus, multiply this back out, A B naught, plus, get rid of the A naught, and so I've just got B naught, C, D naught. So the question is, are these two things the same? Well, we've got the AB naught, we've got the AD naught, and we've got the B naught, CD naught. Looks like we did it good. All right. So again, there's going to be some people that like this better than the Boolean, but you still need to know both for the exam. Thanks for watching.